Our last speaker today is Professor Valeria Nicolosi from Trinity College Dublin. She's a nanotechnologist, and I actually visited her center some time back, and they have a very interesting, very strong interdisciplinary activity in Trinity College in nanomaterials, crossing lots of discipline boundaries. And Valeria is going to talk to us today about 2D nanomaterials in the context of energy.
Thank you very much. First of all, I would like to thank the organizing committee, Judith for inviting me, Tony and the whole board for organizing this wonderful event. So I'm delighted to be here and tell you a little bit about the research that we do at Trinity College Dublin. So what we do, I lead a group, a fairly large group. We're about 25 people. And we do cover everything from material synthesis, 2D material synthesis, very, very detailed atomic resolution characterization, and we are extremely focused on devices. And I'm going to touch upon every single aspect of this work. So our work with two-dimensional nanomaterials started straight after Andre Geim and Kostya Novoselov discovered graphene with the Scotch tape method. You're going to hear Andre's lecture in a couple of days. He's going to talk about this much more in details. At that point, I had just finished my PhD, and I had worked pretty much all my PhD with carbon nanotubes. And I was able to transfer pretty much everything I had learned about making dispersions out of carbon nanotubes to graphene. So I basically, straight after my PhD with Johnny Coleman, we developed what is nowadays being called liquid phase exfoliation. So we identified a theory and a way of selecting organic solvents was surface energy matches the surface energy of a material to exfoliate. And then once you do that, you just need to provide a little bit of energy, shake and stir. At the beginning, we used ultrasonic energy. And then all you need is just starting from a layered material. We start with graphite. And then what you end up with are very, very nice and stable dispersions, in this case, graphene. And the work continued a few years later, where we partnered with Thomas Swan, a company based in the UK, and we managed to upscale the process. And now Thomas Swan actually sells graphene produced this way. So this was our very, very first semi-pilot type of upscaled version of our ultrasonic bath. This is a shear mixer. And that was the first 2,500 liters batch. So the thing is, we moved straight after that. Actually, I made oops. We moved very recently after applying this method to graphene. We were able to really apply the same liquid phase exfoliation methodology to hundreds of other layered crystals in nature. Transition metal oxide, chalcogenides, and the ones you want. So the method is actually based pretty much on the same. And from this snapshot here shows the sort of variety of different materials we can exfoliate. As a first thing that everyone notice is the different colors. Different colors already correspond to different optical properties. And on top of that, some of these materials are metallic, some of these materials are semiconducting, with all different band gaps there. Some of them are insulating, some of them are brittle, some of them are mechanically very strong. So actually, what you have there is a palette of different materials you can choose from in order to make your devices. And that's precisely what we do. In addition to that, in the last decade, we've been starting to work with a fairly different class of 2D materials. Comes from max phases, ceramic materials based on transition metal, carbides, and carbon nitrides. In this case, these layered crystals are quite special because what holds together the crystals, the interlayer spacing, is actually made of very strong covalent bonds. So what we do is we use either HF etching or other acidic type of etching, where we can make this sort of accordions. Effectively, we etch away the middle layer in this ceramic material, so aluminum in this case, and we come with, what we get are this sort of accordion type of structures. Once you do that, actually, what you can see is that this becomes extremely well dispersible even in water. So forget about all the high boiling point organic solvents that you need for more classical van der Waals layered crystals. In this case, only what you get is water, and there what you get is a very, very nice stable dispersion. What I will refer to later on as an ink. This is because once you do the etching, you end up with a lot of oxide groups, OH groups, fluoride groups, and these are actually the ones that make most of this material. Maxins, and in this case, titanium 3C2, titanium carbide, becomes an extremely good electrical conductor, mechanically very strong. So I'll show you some of the applications we are chasing. The thing is, we have all these materials. The thing is, for us, becomes crucial to identify their atomic structure, because defects become extremely important. So we really need, what we do in my group, a third of my group actually is dedicated exclusively into characterizing the atomic structure of the materials and the devices that we make, so that we can then make structure to properties correlations. And this is quite crucial. What I'm going to show you is actually all work coming from our Neon UltraStem, a microscope that I had the pleasure to design myself with Neon. So it's kind of unique. So this is, I don't know how many of you are familiar with STEM, is a scanning transmission electron microscope, not the classical TM we are all used to. So what we have here is a sort of donut-shaped electrode, and what we are detecting here is Rutherford bus scattering electrode, effectively. So when you see bright atoms in your image, you don't need very cumbersome interpretation, very difficult interpretation. The intensity here scales with the atomic number of what you are detecting. So heavy atoms will show bright, lighter atoms will show darker. So actually, this is one of the first works that we did with molybdenum disulfide, and we learned a lot. We learned from this what to use these materials for. So as you see the typical honeycomb type of structure, but one of the most important take-home messages from there was the stacking behavior is quite different. So actually, from liquid phase exfoliation, you hardly see these 2D sheets that are very uniform and very defect-free. Our 2D materials are a mess. We have loads of defects, you have thinner areas, thicker areas, you have a lot of add atoms being there because we actually use organic solvents, and often this is what they leave behind. And you can tell actually from these two zoomed in versions, here, for example, the stacking is slightly shifted. So you have a lot of stacking anomalies and a very unclean type of material. So from this, we actually realized that maybe these materials produced this way are not excellent for making transistors or to explore their pure electrical properties. But we actually can explore the fact that we can make plenty of, as a reinforcement, for example, or for other types of applications, as I would focus later on for batteries. What we did, for example, here with boron nitride, which is isostructural to graphene. In this case, you have boron atoms are alternated with nitrogen atoms. We could actually do a sort of atom by atom mapping. You can see this sort of hexagons where you have the 3 nitrogens and the 3 boron atoms quite distinctively being seen. But you can also see some deviations. For example, for the trained eyes here in the audience, you could perhaps spot that this hexagon here, these atoms, are darker than the nitrogen atoms. And if you do an intensity profile, you actually realize that here is a boron, nitrogen, and then you can actually fit, and this is actually corresponding to carbon atoms. And full ring of boron nitride was actually replaced with carbon atoms, probably coming from the solvent we had used, NMP. You can actually also see that there are much brighter atoms. In this case, this is brighter than nitrogen. And again, you can do the same things, and that corresponds to an oxygen in that side. So from one single image, you can really spot on atom by atom the type of, you can analyze with atomic resolution the types of atoms and substitutions that you have. And we also learned that the more carbon atoms that you add, and carbon atoms always replaced pairs of boron and nitrogen, while oxygen always replaced nitrogen atoms. If you add more and more atoms of carbon, if you dope more and more with carbon, you actually close the band gap. So from a wide band gap semiconductor, typically an insulator, boron nitride, you can actually close the band gap quite substantially. So this is something that was done for the first time back in 2010, and was quite of a unique characterization tool that we developed. We also look at very defective areas. This is a sort of very rough image. As you can see, there are atoms popping, moving positions, and this happens more in the very defective areas. And this is what we are interested in. In fact, what we do is we use these defective areas. I'm not sure whether the lighting is right, but you can even see that you can use those defects to grow lines. This is on a boron, on a black phosphorus layer. And actually, this is the type of lines we were growing in the previous in situ experiment. What is striking is the type of detail and precision we can actually draw. These are copper lines on black phosphorus sheets. I cannot get too much into details of what we are using this for, because it's a project that is funded by Intel. But what I want to showcase is the type of precision that you can do to control defects and the structure of the material. So once we actually gain the type of information about the structure, then for us is the prime focus of the group is to go on to applications and really look at the type of devices that we can develop. So I will make a few examples. The first example that I want to showcase is around our battery work. When you talk about batteries, effectively there are two main goals that very, very basically you want to achieve. One, you want high conductivity, because the electrode, of course, has to carry charge. But of course, also what you need to do is just work on the mechanics of the electrodes. Higher electrodes end up storing higher energy densities. The thing is, the bottleneck of the industry is that you can actually go up to a certain thickness of your electrodes, above which you reach what we call the critical crack thickness. Effectively, what becomes is that the electrodes are not freestanding anymore. And this becomes a huge problem, and this is why batteries, lithium-ion batteries, reach the limit that we all face. So what we decided to do in the first place was starting to work with a very, very promising electrode material for anode, which is silicon nanoparticles. And it was a very, very well-studied anode material at theoretical level. In fact, in practice, it's a material that only lasts in pure form only probably much 10 cycles. The reason is because when you charge and discharge, the material goes into what we call a volumetric expansion and then compression of about 400 times. And once you do it a few times, this becomes completely pulverized. So what we decided was, well, let's see if some of our 2D materials can actually make the trip. The conventional way of improving the mechanical stability of this electrode made out of silicon is actually, the classical way is quite rough, quite rudimental. They use the active material, silicon nanoparticle, carbon black to make it conductive, and then a polymeric binder. And the improvement is not really huge. You might go from 10 cycles to probably 50. And our approach instead was to hit two birds with one stone, using a 2D nanomaterial, MaxSins in this case, that is electrically very conductive and also mechanically very robust. So that's exactly what we did. We used exfoliated MaxSin inks like the ones I showed before, and we added, simply by slurry casting, we made a viscous slurry cast on a current collector, and what we realized actually was the electrode self-assembled itself into what we call a sort of segregated network. So what it means that the silicon particles were completely capped and entrapped within blankets of 2D materials. And this became really the advantage. In this case, I just showcase very quickly the type of achievements that we get. So by adding just 30% of MaxSins in weight, we get an improvement of about 1,200 times the conductivity. We tried different types of silicon, but pretty much the improvement was pretty much substantial in all of those. And this becomes also resistant to bending. The other advantage is on the mechanical properties of the electrode. So we could improve between 15 and 40 times the tensile toughness of the electrode. So from there, we went to look at the electrochemistry. If we look at the electrochemical performance, we can get very nice I-rate response, and this is because we have a very electrically conductive network of MaxSins there. And the very remarkable thing is that we can indeed achieve theoretical capacitance for the silicon particles. So it becomes a very, very important tool. This is pretty much the highlight of this type of work, where if you look at the areal capacitance as a function of the mass loading here, what we get is traditionally, this is the bottleneck that you normally face, is around 4 milliamps hour per centimeter square, while our work goes substantially back up above. So you are pretty much, you go way beyond this threshold. So you deliver a very high areal capacitance, and this becomes important because when you fully assemble a full cell, a full battery, then what you can means is that you actually decrease the portion of inactive materials, the portion of the current collector, for example, or the separator. And that's exactly what we did. We actually built full cells out of this, and indeed we could reach 700 or 800 even for the silicon capped with graphene as well, 800 milliamps hour per gram. This was extremely promising, but then after we published this work on Nature.com, Nokia Bell Labs came to us and said, well, actually, this is really, really promising. We're really interested in this. Can you do similar things with materials that are mass-produced or produced in much higher quantity? Because MaxSins are pretty much at a lab level so far. So what we did was, well, actually, we went on our range of materials and we tried the most upscaled one at that point, which is carbon nanotubes. We did that, and we realized that once you do, if you actually can if you can balance the mass loading of carbon nanotubes, you can still achieve the same segregated networks we discussed about. But this time, these blankets were not formed by 2D MXenes, but 1D carbon nanotubes. And the results were quite outstanding, actually. In the same case, we could massively improve the toughness of the electrode with very minimal amount of carbon nanotubes. So this actually worked for silicon, but also for many other standard electrode materials like LTO, NMC, which are on the cathode part. And this is perhaps the most striking achievement in this case. The fact that if you look at the conventional way of making electrodes with carbon black and a polymeric binder, the three-element system that we discussed before, you actually achieve already the critical crack thickness of the electrode already at about 280 microns. While with our method of the segregated networks, you go up to and above 800 microns. So the more material, the more thickness, the more material, the higher is what you can store. And this is really what we achieved. We actually tried this method both on the anode with silicon and in the cathode, just taking a very standard nickel, manganese, cobalt type of cathode. And in both these works, we could easily achieve theoretical capacitance. So that was it was quite an achievement. And then when we built the full cell, what we realized is that thick electrodes yield to high capacity and high cells, and the performance of the full cell is about 6 times above what a conventional system, a conventional battery is capable of in the market. So you get about 29 milliamp hour per centimeter square. If you look at where we stand with this type of work, which now Nokia Bell Labs has taken to the next level, we were just limited by rate. Of course, very, very thick electrodes lead to very slow charge and discharge. And another thing to improve is the cycling performance, but that is more got to do with electrolytes. Another example for battery applications around 2D materials is the work that we did with antimony, which is another covalent bonded type of material where through crafted synthesis, we can make very, very nice sheets. And the reason why we looked at this material is that because it allowed us to move on to more sustainable type of battery technologies. In this case, we looked at potassium-ion batteries. And again, once again, one of the issues to solve there is the volumetric expansion and compression. So this massive stress from this very high volume expansions. Another thing that we focused on is the electrolyte design for the solid electrolyte interface formation. And we wanted to get away from a flammable type of electrolytes. So this is the type of materials we work with. In this case, I keep jumping. In this case, what we wanted to go away from was the flammability of some electrolytes. So we designed some TFSI type of salts with 3-methyl phosphate, 3-ethyl phosphate, and the fluoroethyl phosphate. And we picked those ones because as you compare with the more classical ones, these 3 are not flammable at all. And they have a very nice electrochemical stability, ionic conductivity, so they ticked all the right boxes. And we looked at the performance. Again, this is a lot of electrochemistry. Don't focus on that. The take-home message here is that, indeed, if you look at the 3-methyl phosphate actually didn't work at all for us, at least in the first instance, while the TFP and the TMP actually worked extremely, the TFP and the TEP worked much, much better. And this is the reason why, if you look at the post-mortem, at the pre and the post-mortem characterization of the electrode material, you actually see that in the 3-fluorophosphide here, you actually see that the structure is pretty much retained, a very nice solid electrolyte interface being formed. Same thing in the TP, although there is some degradation after cycling. The TMP actually was the one that where we had more issues with, especially with oxidation. In this case, we realized that the biggest problem there was the low concentration. Once we went to an higher concentration of electrolyte salt, then we managed also to improve the performance also. I want to switch gear. I want to give you another example, in this case for supercapacitors. Again, not sure how many of you are familiar with supercaps. This Ragone plot, specific power on the y-axis, specific energy on the x-axis, tells you basically how can compare with batteries. So batteries store much more energy, but are very slow at charging and discharging, while electric double-layer capacitors or supercapacitors can store much less energy, but can charge and discharge within fractions of seconds. So this is the second type of application that we targeted for our materials, especially for looking for high rate performance. And this is the first example of applying Maxine inks to produce fully transparent, flexible, and fully assembled flexible devices. So here you already have a cathode, an anode, an electrolyte here, and you can see the transparency that we achieved, and here is overimposed on my postdoc John mobile phone. Quite astonishing is the rate performance. You can go to very, very high rates, and you still see a very quasi-rectangular CV graph where showing basically pretty much no resistive behavior. And we went a step further there. If we have these nice inks, then we can actually think about prototyping our devices quite fast so that we can test them routinely before we get into cumbersome assembly. So what we did was we used common 3D printing to produce stamps of any shape and form. And then what we simply do to test the material in the first place is dip in the ink and stamp. And what we get is these nice devices stamped on paper, for example. And once you do that, you realize that the one simple dipping is already making supercapacitors that work extremely nicely. At 200 millivolts per second in scan rate, you start getting some resistivity, but otherwise they work extremely nicely and they're fully bendable. The cycling performance, you can actually push 10,000s of cycles without any loss in performance. And from there, we made a push further as well. We kind of started feeding our inks into the stamps, and we managed a way to prototype tens and tens of devices that then we can average in performance. Having inks also allows us to explore inkjet printing capabilities. This is the nice thing of having inks in solvents that we control. We can control the rheology. So what we developed are both extrusion printing methodologies and inkjet printing technologies, depending really on the type of solvent that you're using and the type of rheology that you have. And we use those to produce all Maxine supercapacitors. So these are just some examples of Maxine devices in series, in parallel, all with interdigitated geometry. These are printed on plastic, and these are from water, while these are from organic solvents, NMP. And you've seen the video. I show that you can use Scotch tape. Once you put them down, they're pretty mechanically robust. They're there to stay. We have devices that have been there pretty much a year long. And from there, we could manage even to push 3D printing technologies. The same concept as before. the more you print, the more material you have, the more energy you can store. So these are some of the geometries of some 3D structures that we have been able to print by aerosol gel printing. And these are incredibly sturdy, actually. They don't collapse. They're pretty mechanically robust. And if you do that, and you compare, for example, the interdigitated devices that I showed you before with interdigitated devices with 3D pillars grown on, then you can see that you can actually improve about 60 to 70% the performance of the device simply by just adding these pillars to the device. Another example of the versatility that we have achieved was to make something different with graphenes. In this case, we started from zinc oxide tetrapod made templates. And then once you make these templates, and we can make them with any shape and form, what you can do is this is supposed to be, yeah, there you go, a video where you can simply coat your Maxine dispersion there, remove the excess, and then what you end up with are these tetrapods being covered with Maxines. What you do at the end is just you etch away the zinc oxide, and you end up with hollow tubes made of Maxines. And these are 99% air. That's why we call them aero Maxines. They're super light. You can compress the pillars. And we like these devices. They're all been in the process of being commercialized, actually, as an outcome of this very nice EIC transition grant, because we have two ways of controlling these devices. One is that we can tailor the nanostructure of these tubes. How? Simply by dipping more Maxine dispersion onto the template. So you can make these walls thinner or thicker, depending on the type of performance that you want in your device. But also what we can do is we can tailor the microstructure just by applying pressure and making these discs more dense. And if you do that, you can really have an easy tool to control density as a function of aerial loading. If you do that, then you build a system that can be tuned and templated depending on the type of performance that you want to get out of the device. Not all the electronics will require the same type of super cap. So effectively, if you want an high gravimetric capacity, or if you want to pursue more aerial capacitance, then you can actually tune what type of device you make. Another thing that we have done, again, using the versatility of our devices, is to build these devices to print them directly on textiles. And this is a project that we currently have with an industrial partner. They want to pursue the e-textile technology. The company is Logitech, and this is really focused on e-gamers to give them more freedom and an higher experience. But effectively, this is a type of technology that you can think being applied for many other things in health, in sports, monitoring, heart rate, and so forth. Same concept, the freedom that you have to print on any sort of substrate. Here you see these devices in parallel or in series being printed on cotton. We have printed on cotton, polyester, lycra, pretty much any sort of textile you think. And we can retain the very nice bending capabilities and the very nice capacitance. This is, again, what happens to the devices in terms of scan rate performance. The nice thing is that the bending test that I was telling you basically can bend and rebend again, and the electrochemical performance is retained. Being all printed, you have the additive manufacturing freedom there, which means that you can actually make asymmetric devices as well as symmetric devices. And by going to asymmetric, you end up increasing the potential window that you can get. Last but not least, we did in this case some washability tests, ISO certified, and we basically saw that you can actually push hundreds of washes and the electrochemical stability of the device is still retained. So you have some decay from the first 5 cycles of washing, and then it stabilizes and the performance is retained. Another example of the freedom in application space that we have is on mixing Maxine inks with P.PSS, for example, adding some additives such as dimethyl sulfoxide, sodium ascorbate to stabilize the material, and we make hydrogels. Hydrogels that are fully printable, and which again we use very successfully with a very good success as supercapacitors. So again, this is a nice plot where we show the retention of the capacitance as a function of mass loading, and this is the type of performance of these devices. And last but not least, want to switch gear on one very different type of application that we are pursuing in my lab, and it's in the electromagnetic interference shielding domain. It's a very, very hot topic, of course, and what we can do is, using the properties that Maxines have, with suitable polymers like polyacrylic acid in particular, we couple them with amorphous calcium carbonate, of course, to stabilize the system towards oxidation. And the nice thing that we achieve is that these hydrogels have this very nice hollow structure, which is the reason why they're very successful at electromagnetic interference shielding. Here you see an identical film without Maxines. You see the terahertz domain type of spectrum, and only by adding 6.5% of Maxines, you already have a sort of 99% screening of this emission. The nice thing also comes from the fact that these type of hydrogels are very printable and completely stretchable and healable. So they can adhere to pretty much to any surface, and they are self-healable as well, which means that you can recombine them, and of course they retain their electrical conductivity. One thing that we've also used them for is for motion sensing. So this is, for example, one of these hydrogels been really stuck on the finger of my postdoc, and you can actually detect the bending on of the hydrogel, in this case, because you corrupt the percolation of your sheets in the polymer. So you change the electrical conductivity. So in this case, you can also detect the arm bending, you can detect the different phases of swallowing, if you have it here in the trough, forearm, frowning of the forehand, pressure sensing for water droplet being dropped on the film, and you can even use it to censor writing. Very small words, but again, is good as a proof of concept. And of course, they are very, very nicely printable type of inks by extrusion printing. Last but not least, I want to showcase some examples of some things that have already made it to our collaborators. So this is a partnership with Lego. We managed to use some 2D materials inks to make their Lego blocks electrically conductive. This intellectual property was transferred to Lego. They bought the patent, and they are currently doing all sorts of tests that they normally would do, saliva tests for the kids and so forth. Another example is partnering with Grundfos, a company that makes pumps. And they wanted 2D materials-based hydrophobic surfaces. Again, this is another example of some very basic research that was pushed to industry. And this is another collaboration quite a while ago with a Formula One team, which I cannot name, I cannot disclose, but I might give away some hints later. But they came to me after, I think they might have seen an article or saw me on TV, I cannot remember. But they basically came to me and say, well, can some of your 2D materials be used for a heat transfer? What we want is just a material that can coat the rim of our tires and can make us achieve the right temperature as soon as possible, because that would play as the pole position. And so we did partner with them, and in fact, we gave them the improvement that they wanted. And as I said, I cannot say who the partner is, but I can say that every year I get to see the Formula One from a very, very special place in Monza. And this is really what it takes them to change a set of tires. I think a video took the last Formula One Grand Prix Monza from the paddock. So this is just a snapshot. Another collaboration has been with JVC Kenwood, and they're making loudspeaker membranes out of 2D systems. Again, I cannot disclose which materials, but it's just to showcase some of the things that we have done already in partnership with industry. So I hope I have convinced you about the versatility that we have and the promises of these 2D materials and the type of detail that we have and hands-on that we have in tuning the properties of these materials to target the type of devices that we want. I can, last but not least, this is my group. I'm very, very keen in showing them because I get to spend very, very little time in the lab. I do my science through their hands and through their eyes. So they are the people who really deserve the acknowledgement. And of course, I need to acknowledge all my collaborators. It takes a full house to achieve work, and of course, funding. And I thank you once again for the invitation and for the great audience. Thank you.